second generation being built up right now and tested down in the lab, and shown that what the capabilities for that system should be when we deploy the AMP in marine energy environments. Tested a relatively novel way of performing hydrodynamic coefficient measurements, and the benefit of, or the type of dynamic simulation you can do to determine the operational limits in turbulent currents. This is a picture of the system being deployed off the back of the RV Jack Robinson back in February. And going forward, we have a little bit more field testing to do this month at the end of May out off Marrowstone Island, and there's hope to, after that over the summer, AMP will be deployed for a long term, probably for at least a month out in Squim Bay. And Brian has a couple other students working on instrument integration, and we have ideas for how we might be able to use these types of simulations and to develop autonomous deployment capabilities, which would be a project in the probably distant future, but an idea that we have. And during the field testing in May, we're hoping to potentially collect a little bit of data to help benchmark the simulation performance. And if all goes well, potentially spin-off company called Mauricio to provide monitoring services to the developing industry using this technology. And I'd like to thank all of you for coming here today, and especially to my committee for helping me through this process. It's been great working with all of you over the last 4 years. Yeah. Any questions?
Simulations of just an umbilical cord and of just your thing and combine those two?
I kind of did that actually. So the reason the umbilical simulation takes so long is because throughout that simulation, the software is calculating all of the forces acting along the length of the umbilical. And with turbulence, those forces are fluctuating constantly. And the simulation has a dynamic time step that slows itself down if the forces are changing rapidly. So inherently with turbulence, it's slowing down the simulation and taking longer. I did another set of simulations which I didn't talk about here, which instead of having the umbilical pulling on the back of the ROV, there was a constant force acting on the back of the ROV. And I did another simulation with ROV fixed in place and an umbilical coming off the back of it at a fixed length to determine how much force on average the umbilical is imparting on the ROV in a worst case scenario. So with the ROV about 30 meters out or in front of and 5 meters off to one side of the launch platform. And that measured it gave me a tensile force of only about 20 newtons, which is pretty low. Compared to the force that you see on the whole system. In general, if you look at the surface area of the ROV that with the setup, it's only about 6% of the overall system. Yeah, then I did the same type of simulations with just that constant 20 newtons of force pulling on the back of the ROV and saw the same results as with very, very similar results to the simulations with the full umbilical.
Towards the end, you went back and compared your experimental results, your CFD, with canonical values. Were those canonical values for a simplified geometry of the sub, or where were you getting those from?
Yeah, there's no sort of canonical values for this type of geometry because it's too unique. But I basically said if you had a rectangular solid that had the same, so there are canonical values for rectangular solids with different aspect ratios. So the length of the rectangle versus the frontal area of the rectangle. And considered, or figure out what those were for a system with that frontal area and that length. And so basically approximating it as a rectangle.